Hello viewers, welcome to this exciting video. This is a lesson video and not a revision video. So the first lesson that we will look at is actually coming from the topic current electricity. Now current electricity is a relatively short but long topic. The reason why I've said short and long is because the content itself isn't that much. However, what is involved is a lot, and we really need to pay very particular attention to small details that we will look at. Now, before we even get the ball rolling, looking at current electricity, we need to understand certain terms that are used in the study of current electricity. So terms used. So what are the terms used in the study of current electricity? The first term that we will look at is electric charge. Electric charge. Now, what is electric charge? So basically, electric charge, this is a physical property an elementary particle has that enables it to experience a force when it is placed in an electric or magnetic field. So we will say this is the property an elementary particle has that makes it experience a force when placed all right. So basically what we're saying is that whatever this property is, it actually makes the particle undergo a force when it is placed in an electric or a magnetic field. Then we can actually now look at the unit of this property, because if it is a physical property, then it is measurable. If it is measurable, then it should have a unit. So the unit of electric charge is a coulomb. A coulomb. Coulomb is symbolized by the capital letter C. So a coulomb is denoted by the capital letter C. Okay. Then we can now look at the types of charges. The types of electric charge. So basically, there are two types. There are two types of electric charge, and these are positive positive and negative charges. All right. Now, Since we only have two types of charges, and that is positive charge and negative charge, let's try to dig in deeper, a little bit deeper into these charges. So let's look at a positive charge. Okay. So basically, positive charge. Okay. Uh, a positive charge actually comes from the elementary particle found inside the nucleus of an atom. So basically, we actually talk about positive charge being the charge possessed by a proton. So this is the charge that comes from protons. Now, if these are charges coming from protons, how much charge does each proton have? So each proton has a charge of 1.6 positive. This is positive, has a charge of positive 1.6 times 10 to the power negative 19 coulombs. So each proton has a charge of plus 1.6 times 10 to the power negative 19 coulombs. Okay. How about negative charges? So this is the charge that comes from an electron. So this is a charge that comes from an electron, and each electron has a charge of negative 1.6 times 10 to the power negative 19 coulombs. So basically, this is where these electric charges are coming from. 1.6 times 10 to the power negative 19 may seem to be small. However, we find that one mole of any given substance will have an enormous number of protons and electrons. So we find that in just a small amount of a substance, we've got so much electric charge. Okay. Okay. Having looked at electric charge, we actually now move to the next term that we need to look at. So we've looked at electric charge and what it is, then the types of charges and where they come from. So we now look at the second term, and the second term is electric current. Electric current, I. Now, before I proceed, I think it's better to take note that electric charge, it is good to take note that electric charge has a symbol of small letter q. So the symbol for electric charge is small letter q. Okay? All right. Now we look at electric current, I. What is electric current? So this is the rate of flow of charge. What charge are we looking at? We are looking at electric charge. So electric current is the rate of flow of electric charge. Now, we need to understand this statement very well. The rate. So what does rate mean? It means that how much, or how much of a given substance, okay, uh, is, let's say, passing through a given point every given time. So rate is just how much is passing, let's say, every second. How much is passing every second, or how much is passing every minute, how much is passing every hour. So if you look at how much in relation to time taken for that substance to actually do that, we are actually talking about rate. So this is the rate. So rate always involves time. Okay, so how much in a certain period of time is rate. So the rate of flow, how much charge is flowing through a given point over a certain period of time. How much charge is passing through a given point in a given space of time. So that is what current is. So unit. Okay, what is the unit of electric current? The unit of electric current is the ampere. Ampere. The ampere, and it is denoted by a capital letter A. So electric current is measured in amperes. Okay, and how do we denote an ampere? An ampere is given by a capital letter A. So an ampere is given by a capital letter A. All right. Then instrument. We now move to instrument. Instrument. It is important to note that any physical quantity, because a physical quantity should be measurable, and anything measurable obviously will have something that we can use to measure it, and that is why I'm emphasizing so much on the unit and the instrument. So what instrument is used to measure electric current? So electric current is measured using an ammeter. An ammeter. So an ammeter is the instrument used to measure electric current. Ammeter. So an ammeter is the instrument. Now, what is the symbol in an electric circuit of an ammeter? The symbol of an ammeter is a circle, okay, with contacts on both sides, and in the middle of a circle you have a capital letter A. So if you see this kind of symbol in an electric circuit, then you know that that is an ammeter, and the ammeter is used to measure electric current. However, an ammeter is not connected in any particular way that a person feels like connecting it. An ammeter is always connected in series. In series with other circuit components. So an ammeter is always connected in series with other circuit component. Let's say we have a circuit, okay, comprising of a cell. So we have a circuit comprising of a cell, okay. To this cell, a lamp is connected. In this circuit, a lamp is connected. Now, if we see a cell like that, usually the short terminal, that side, is the negative, and the long one is the positive. And current, should always be noted that current flows from the positive terminal, okay, to the negative terminal. So electric current will move from the positive terminal, come and pass through the lamp. So this is our lamp, okay, and back to the cell. So this is our cell. However, if we wanted to measure the current flowing through the lamp, it means that we now need to connect an ammeter, okay, to this circuit. So how are we going to connect it? Since we are saying that it should be in series, so we're going to have our cell there, okay? We're going to have our cell, and to this cell we are going to connect. So we are going to connect an ammeter, and from the ammeter, the other terminal of the ammeter should be connected to the lamp, and the other terminal of the lamp should be connected back to the cell. So we have our ammeter there. So because one terminal of the ammeter is connected to the cell, while the other terminal is connected to the lamp, it means that the ammeter is in series with both the cell and the lamp, okay? Because one terminal is connected to another circuit component while the other is connected to another circuit component, means that the ammeter is connected in series. And this is the correct way of connecting an ammeter, okay? This is the correct way of connecting an ammeter. Let's look at the formula for calculating electric current formula. Okay, so if we wanted to calculate the electric current flowing through the lamp in our circuit here, okay, we are going to use the formula. So we're going to use the formula current I is equal to charge, electric charge, Q, divided by time taken for the charge to actually pass through. So time T. So therefore it is going to be I is equal to Q over T. So this is the formula for electric current. Okay, this is the formula for electric current. Okay, we can actually have one example on how to calculate electric current. Okay, and in this example we're going to have All right, so we have studied the circuit below. So this is our circuit, and we have, if 10 coulombs of charge passes through the lamp every 20 seconds, what is the ammeter reading? If 10 coulombs of charge passes through the lamp every 20 seconds, what is the ammeter reading? So to actually find the ammeter reading, uh, the ammeter measures current. So we are looking for current. Okay, and what have we been given in the question? We've been given, so the data that we have, is, we've been given electric charge, which is 10 coulombs. We've been given time, which is 20 seconds. But the question requires us to find electric current. So electric current, we don't know. But we have an equation that has these three quantities. So we have an equation that has got I, which is current, time, and charge. So we're going to use that equation, and the equation is current is equal to charge divided by time. So we are going to have current is equal to 10 divided by 20. Okay, 10 coulombs divided by 20 seconds. This is going to give us 10 divided by 20, which is 0.5. So we have current is equal to 0.5 amperes. Now we can see that in our equation for current, on top we've got coulombs and down we've got seconds. So we can also say that the alternative units for current may be coulombs per second. And sometimes examiners will play on our minds by actually putting 0.5 coulombs per second, and we think the answer is not there, and they'll put other common units such as volts, watts, and we may rush into choosing those. So it is always important that we take note of the alternative units. So that is the ammeter reading. The ammeter reading is 0.5 amperes. All right. Maybe it is equally a good idea. It is equally a good idea that this becomes example 1, and we also look at another example, which will be example number 2. So example number 2 will be basically 0.2 amperes, okay, flows through a circuit for 5 seconds. So 0.2 amperes flows through a circuit for 5 seconds. How much charge flows through the circuit during the 5 seconds. So how much charge? So in this particular question, we have 0.2 amperes flows through a circuit for 5.0 seconds. How much charge flows through the circuit during the 5.0 seconds. So what we've been given, which is our data, what we've been given in this question is that we've been given electric current I, which is 0.2 amperes, and we've also been given time, which is 5.0 seconds. And the question requires us to find charge, which we don't know. So again, we actually, after extracting the data from the question, you ask yourself, is there an equation that actually has current, time, and charge? Again, yes, we have an equation, and the equation is current is equal to charge over time. So we will directly substitute, okay, and we are going to have 0.2, okay, is equal to charge, which is Q, we don't know, over time, which is 5. Okay, now what we're going to do is that we're going to say 0.2 over 1, then we cross multiply. Okay, so it will be 1 times Q, so 1 times Q is equal to 0.5 times, oh, not 0.5, it's actually 0.2 times 5. Okay, so 0.2 times 5. So 1 times Q is Q. Q is equal to 0.2 multiplied by 5, which is equal to 1. So we have 1 what? 1 coulomb. So the amount of charge that flew through the circuit during the 5 seconds was 1 coulomb. Okay, so this is how examiners will play with your mind. Sometimes they may ask time given charge and current. Okay, yeah, so they may ask about how long did it take this amount of charge to flow through a second if the current was this. So we just need to know how to manipulate and work with this formula. All right. Okay. Having looked at electric current, where we are supposed to go is actually looking at cells. Cells. However, we will not look at cells right now. I will dedicate a video specifically on cells. Okay. However, from here, we are going to look at two very important terms. And this third term is, we're going to look at potential difference. We're going to look at potential difference. So, what is potential difference? What is potential difference? So, potential difference, this is the work done in moving 1 coulomb charge across a circuit component. So, this is the work done. So this is the work done in moving a 1 coulomb charge across a circuit component. So work work is measured in joules. Okay, work is measured in joules, and charge has a unit of coulomb. So potential difference in all its form may just reduce to a joule per coulomb. However, when we look at the unit, okay, or before we even look at the unit, it's better we actually understand what this statement means. So if, let's say, in our circuit, in our previous circuit, okay, where we had a cell there, okay, we had a cell and we had a lamp there, okay. Now this is a closed circuit, so we expect our lamp here to light up, okay. Now as charge is flowing through the circuit, now take note of one thing. We said that electric current will flow from the positive terminal to the negative terminal, so electric current is flowing in that direction. However, the electrons are not flowing in that direction. The electrons will move from the negative terminal going to the positive terminal. So this will be the direction of flow of electrons, okay. So electrons are moving in that direction. Now it means that electrons are passing through the lamp in that direction. So when we talk about potential difference, we are just talking about, since electrons actually possess a negative charge, we are actually saying how much energy is needed to actually push 1 coulomb of this electric charge coming from electron across the lamp, okay. So that is what potential difference is. How much work is needed to move a charge of 1 coulomb from point, if we had point A here and point B there, how much work is needed to move 1 coulomb of charge from point A to point B? That is the potential difference. So potential difference is the work done in moving a 1 coulomb charge across the lamp from point A to point B. Or if the charge is moving in the direction of flow of current, it means it is how much work is needed to move that 1 coulomb of charge from point B to point A. Simple and straightforward. I may say simple but straightforward. It may be a little bit abstract because I've actually put two concepts here. Current, which is moving. So this is current moving from the positive terminal going to the negative terminal. And I've also said, however, electrons are moving in the opposite direction to the current. So because electrons possess charge, okay, electrons possess charge, so I actually found it a little bit more convenient to use electrons that have charge to actually explain. However, it is just how much work is needed to move a charge across a circuit component. The circuit component may be a lamp, like in our particular case, or it may be a resistor, it may be um, um, there are so many other circuit components like diodes and so on and so forth. All right, so that is about potential difference. Now, what is the unit for potential difference? The unit for potential difference is a volt. A volt, okay, a volt, which is denoted by a capital letter V. Now, a volt is also equivalent. So it is also equivalent to joule per coulomb, okay, which is capital J over capital C. So this is equal to the big V, which is the volt, okay? So you may find joule per coulomb or just volt. So this is almost one and the same thing, okay? Now, having looked at the unit, it's better we also look at the instrument. What instrument is used to measure potential difference? So potential difference is measured using an instrument called a voltmeter. Okay? Potential difference is measured using an instrument called a voltmeter. And the symbol of a voltmeter, is a circle, okay, with terminals on both sides with a capital letter V. So this is the symbol of a voltmeter. However, it should be noted that a voltmeter is always connected in parallel. Okay, it is always connected in parallel with other circuit components. It's always connected in parallel. What does parallel mean? Okay, in our previous example, when we looked at an ammeter, okay, we said it is connected in series, and in series we said one terminal of the ammeter is connected to one circuit component while the other one is connected to another circuit component. In this particular case, if we have a cell, okay, if we have a cell there, okay, connected to a lamp, if we have a cell connected to a lamp, what we are going to have, okay, allow me to move the diagram, to that point where if we have this circuit, okay, and we have our lamp there, okay. Now, what it means is that parallel means that one terminal of the voltmeter is connected to one end of the lamp, okay, while the other terminal is connected to the other terminal of the lamp. So both terminals of the voltmeter are connected to the same circuit component, which is the lamp. There is no relationship, there is no direct connection to the battery, which is the other circuit component. So this is what we mean when we say parallel. Okay, series means that one terminal is connected to another circuit component while the other is connected to another circuit component. So this basically is how we connect a voltmeter in a circuit. All right, we turn our attention to another, which will be the fourth term, which is electromotive force, which is EMF, electromotive force. All right, now, what is electromotive force? What is electromotive force? Electromotive force is not really a force, okay? Yeah, the term force may prompt one to say it is the force needed. No. It's not the force. It's actually the work, okay? So electromotive force, this is the work done It's the work done in moving a 1 coulomb charge around a closed circuit. So it is the work done in moving a 1 coulomb charge around a closed circuit. Yeah. What does this mean? It means that if we have a cell there and we have a lamp there, okay? If we have a cell and a lamp, it means that the EMF is the work done in moving a 1 coulomb charge from, let's say, if this, let's put this, let's say this point will be point A and this point will be point B. So how much work is needed to move a 1 coulomb charge from point A around and back to the battery? So from point A and up to point B, which means that this charge moves from one point of the battery round the circuit and back to the battery. So the amount of work that is done in moving a 1 coulomb charge around a closed circuit is called the EMF. Now take note, EMF and potential difference are different. If we remember, potential difference will just be the work done in moving a 1 coulomb charge, let's say, across the lamp, which is a circuit component. So from one point of the lamp to the other point of the lamp, that will be PD. However, from the battery round and back to the battery, that will be EMF. Okay, so that is also the difference. Okay, however, both of them are work done, okay, per unit charge. So if both of them are work done per unit charge, it means that they all have the same unit. So if we look at the unit for EMF, the unit will also be volt, which is denoted by the capital letter V, which will be also joule per coulomb. So if we have an open circuit, then EMF not so much, because it should go around a closed circuit, the work done in moving a charge around a closed circuit. So if the circuit is open, then EMF, no. But how do we measure the EMF? Okay, the EMF, the instrument is also a voltmeter. However, this voltmeter, the way the voltmeter is connected, it is not across the circuit component, but across the source. Okay, the source. So if we have a cell there, so this is the source of electric current. Okay, in our previous case, the voltmeter was connected there, V. Okay, if we connect it like this, we are actually measuring the potential difference across the lamp. But in this particular case, we want to measure the potential difference. So we are going to connect the voltmeter across the source of current, which is the cell. So if it is connected like this, then we are measuring EMF, which is electromotive force. When it is connected across across a circuit component uh, like this, then we are actually measuring a PD, which is potential difference. So that is that. All right. Uh, um, we can now look at another term, and this term is resistance. Resistance, electrical resistance. I've even lost track of what. So this is term number 5, which is the fifth term. Electrical resistance. R. Electrical resistance. So electrical resistance R. What is electrical resistance? What is electrical resistance? So electrical resistance is simply just the opposition to the flow of current. The opposition to the flow of current. So whenever there is opposition to the flow of current, then we have electrical resistance. And regardless of the situation, in most of these circuit components, these conductors, we always have opposition, which is resistance. And electrical resistance is measured in units uh, units called ohms. So ohms. So the ohm is actually the unit for electrical resistance. Ohm. So the ohm is the unit for electrical resistance, and it is denoted by the Greek letter omega. So the Greek letter omega is the symbol for electrical resistance. So electrical resistance is denoted by the Greek letter omega. All right. At this particular point in time, we will now look at factors that affect electrical resistance. So factors that affect resistance. What are the factors that affect electrical resistance? Okay. The first one will be temperature. Temperature. So temperature affects electrical resistance. And what is the relationship between temperature and electrical resistance? The relationship is that the higher the temperature, the higher the resistance. So the relationship between temperature and resistance is that temperature is directly proportional to resistance. So temperature is directly proportional to resistance. Okay. In mathematics, we will have T is proportional to R. So this is the relationship. The higher the temperature, the higher the resistance. The lower the temperature, the lower the resistance. Basically, this is the reason why we actually switch off electrical appliances when we feel that their temperature has increased so much. Because the resistance increases, we actually will expect the electrical component to actually get burnt or destroyed. The second one is actually length of the conductor. Length of the conductor. The length of the conductor. Okay? And what is the relationship between length of the conductor and resistance? Okay? The longer the electrical conductor, the higher the resistance. So even in this particular case, the relationship is a proportional, a direct proportional relationship. The longer the conductor, the higher the resistance. So length is directly proportional to resistance. So length is directly proportional to resistance. Length is directly proportional to resistance. Length is directly proportional to resistance. Again, we have L, oh, not equals, proportional to R, is directly proportional to R. And to just say, to just have a diagram there, we can also have a diagram like that, where we have, this is conductor A, and we can have conductor B. Okay, conductor B. Okay, they all have almost the same cross-sectional area. Okay, so this one has high resistance. This one has low resistance. And the reason is because of the length. The longer the conductor, the higher the resistance. The shorter the conductor, the lower the resistance. All right. Then we go to the third factor, which is cross-sectional area of the conductor. Now, what is the cross-sectional area? It's more like the thickness of the conductor. Okay, so the thicker the conductor, the lower the resistance. The thinner the conductor, the higher the resistance. So in this particular case, we'll just say, okay, diagrammatically, we can have conductor A, okay, conductor A, and conductor B. All of them with the same length. Okay, the length is the same. However, this one is thicker than this one. So this thick one has got low resistance. This one has high resistance. When we look at cross-sectional area, we can actually look at a situation where we got maybe people in let's say a hall. Okay, people gathered in a hall, and in actually two halls. Okay, now one of these infrastructures has got very big doors. Okay, and the other one has got very small doors. Okay, and in each one of them we've got, let's say, 1,000 people. We now ask ourselves, which of the two structures, okay, in which of the two structures will people evacuate faster than the other? obviously, in coming out of the hole, it will be easier for people to come out of the hole with a bigger door, okay? With a bigger door than one with a small door. So it will be difficult for people to come out of, it will be easy for people to come out of A than people to come out of B, because this door is small, okay? So it will only allow a small number of people to pass through, so hence higher opposition to people moving out. While this one with a large door will allow more people to come out, hence the lower the resistance. So we can actually take it like that. All right. Having looked at electrical resistance and the factors that affect electrical resistance, we actually can end here for now. However, in the next video, we will look at resistors as circuit components. So for the terms that are used, we are just remaining with, I think, one term that we really need to look at, and that is electrical power. Okay, electrical power. That is the term that we are remaining with, and it will be tackled obviously in the second or in the third video on current electricity. Thank you very much. If you are a new viewer, please, if you like the content, don't forget to subscribe and hit the notification button. Thank you very much.